Have you ever wondered where stars are born? And could it be that the smallest galaxies in our universe actually hold the largest star factories? Let's dive into the enigma of the universe's smallest galaxies, the dwarf galaxies, and their surprising role in star formation. Imagine a tiny, seemingly insignificant galaxy, far smaller than our own Milky Way. It's easy to overlook, right? But, as it turns out, these dwarf galaxies may be the universe's most prolific star creators. A recent study has turned our understanding of star formation on its head, suggesting that the most intense regions of star creation are not in vast galaxies like ours, but in these tiny dwarfs. Now, you might be wondering, how is this possible? Well, the stars in dwarf galaxies are more likely to turn into black holes rather than explode in supernovas. This is a crucial detail because supernovas have a significant effect on star-forming material. They often blow away this material, preventing further star formation. But in dwarf galaxies, there's a delay of around 10 million years in this process. This delay allows these galaxies to retain their star-forming molecular gas for longer, fostering the growth of star-forming regions and, consequently, the production of more stars. In contrast, in more massive galaxies like our Milky Way, where more stars explode in supernovas, the powerful winds created by these multiple explosions can blow out the remaining molecular gas, putting a damper on further star formation. But dwarf galaxies, with their lower metallicity and fewer metals, experience a delay in the onset of these strong superwinds, leading to higher star formation rates. This study, led by the brilliant minds of Michelle Jeckman and Sally Oey from the University of Michigan, not only provides insights into star-forming conditions in dwarf galaxies, but also offers implications for understanding the early universe's first galaxies. Quite intriguing, isn't it? The smallest galaxies harboring the most robust star generators. As we delve deeper into the cosmos, we continue to uncover its many mysteries, and in doing so, we're reminded that often the most significant wonders come in the smallest packages. To understand this paradox, we first need to grasp the phenomenon of star formation in these miniature galaxies. Now imagine a bustling star factory churning out new stars with a fervor that defies their small stature. This is the reality in dwarf galaxies. The process of star formation here is both fascinating and distinct. Stars in dwarf galaxies are born from vast clouds of gas and dust. As these clouds cool, they begin to collapse under their own gravity and pockets of dense material form. These pockets serve as the birthplaces of stars, but here's where the peculiarities of dwarf galaxies come into play. Unlike in more massive galaxies, stars in dwarf galaxies are more likely to turn into black holes than explode in supernovas. You see, a supernova is a powerful explosion that occurs when a star has used up its nuclear fuel. This process scatters elements across the galaxy, creating a powerful wind that can blow away the remaining star-forming material. But in dwarf galaxies, this explosive end is less common. Instead, these stars often collapse in on themselves, forming black holes and leaving the surrounding gas and dust relatively undisturbed. This divergence in stellar fate leads to a delay in blowing away the star-forming material in dwarf galaxies. We're talking about a 10 million year delay, which, on a cosmic scale, is the equivalent of hitting a cosmic pause button. This delay is crucial as it allows dwarf galaxies to hold on to their star-forming molecular gas for a longer duration. The retention of this molecular gas encourages the growth of star-forming regions, essentially creating a fertile ground for the birth of new stars. It's like providing a plant with the right amount of water, sunlight, and nutrients. It flourishes. Similarly, the conditions in dwarf galaxies create an environment where star formation can truly thrive. So, in essence, the delay allows dwarf galaxies to retain their star-forming molecular gas for longer, promoting the growth of star-forming regions. Now let's juxtapose this with more massive galaxies like our very own Milky Way. Imagine a bustling city bustling with life with constant explosions of energy, and you've got a good picture of what's happening in a large galaxy. In these cosmic metropolises, stars are born, live and die in a spectacular cycle of creation and destruction. But unlike the peaceful countryside of dwarf galaxies, the city life of massive galaxies is a bit more tumultuous. When stars reach the end of their life cycle in these larger galaxies, they often go out with a bang, exploding in brilliant supernovas. These supernovas aren't just a spectacle to behold, they're powerful forces that shape the galaxies they reside in. The winds created by these supernova explosions are so powerful that they can blow out the remaining molecular gas within the galaxy. And it's this molecular gas that's essential for the formation of new stars. So what does this mean? Well, in a nutshell, the more supernovas there are, the less gas there is left for producing new stars. This is one of the reasons why star formation in massive galaxies tends to slow down over time. Now let's contrast this with what we've learned about dwarf galaxies. These smaller galaxies have lower metallicity, which means they contain fewer metals. And it's the abundance of metals in a star that contributes to whether it will explode in a supernova or collapse into a black hole. Stars in dwarf galaxies are more likely to turn into black holes than explode in supernovas, and this key difference leads to a fascinating outcome. Because there are fewer supernovas in dwarf galaxies, there are fewer superwinds to blow out the star-forming molecular gas. This results in a delay, a pause if you will, before the gaseous materials are blown away. This delay, lasting for about 10 million years, allows dwarf galaxies to retain their star-forming molecular gas for longer, thereby promoting the growth of star-forming regions and the production of more stars. So, unlike their larger counterparts, dwarf galaxies, with lower metallicity, experience a delay in the onset of strong superwinds, leading to higher star formation rates. The study leading to these findings was not just an academic exercise, it has far-reaching implications. Just imagine the early universe, a time before the Milky Way or Andromeda. A time when galaxies were just starting to form, and the cosmos was filled with these small, dwarf galaxies, vigorously churning out stars. These galaxies were not weighed down by metals, just like the dwarf galaxies we see today. They were small in size, yet their star formation was intense, much like the dwarf galaxies we've been discussing. The research conducted by Michelle Jeckman and Sally Oey with the aid of the Hubble Space Telescope helps us to understand these first galaxies better. By studying the smallest galaxies in our universe today, we get a glimpse into the past, a peek into the early universe. It's like a cosmic time machine, if you will. These dwarf galaxies, with their intense star-forming regions and low metallicity, serve as a living model of the conditions that prevailed in the early universe, the conditions that led to the formation of the first galaxies. By understanding the process of star formation in these galaxies, we are essentially deciphering the mysteries of our universe's origin. Moreover, the insights gained from this study are not just confined to the realm of astronomy, they also have implications for fields like physics and chemistry. After all, the stars are the universe's factories for producing elements. The intense star formation in these dwarf galaxies could have contributed significantly to the chemical evolution of the universe. In conclusion, the study of these dwarf galaxies, their intense star-forming regions, and the delay in the onset of superwinds is not just about understanding a specific type of galaxy. It's about understanding the universe itself, its past, its evolution, and its future. These findings indeed add a new dimension to our understanding of the universe. So, what does this all mean for our understanding of the cosmos? As we've journeyed through the stars in this video, we've discovered that the universe's smallest galaxies, the dwarf galaxies, are a hotbed of star formation. They're the underdogs of the cosmos, small in size, yet mighty in their role. They are the universe's most prolific star factories, churning out stars at a rate that is both astonishing and intriguing. This star-forming prowess is owed to a perfect storm of cosmic conditions. Unlike their larger counterparts, dwarf galaxies don't often see their stars explode into supernovas. The lack of these explosive events means that the molecular gas, the stellar birth material, isn't blown away by powerful winds. This allows dwarf galaxies to hold onto their star-forming gases for longer periods, around 10 million years longer to be precise. This delay in the onset of superwinds, combined with their lower metallicity and fewer metals, creates an environment that's ripe for star formation. The stars keep forming, and the process continues unhindered and unbroken. But why does this matter? Why should we care about the star-making capabilities of these tiny galaxies? The answer lies in the past. The characteristics of dwarf galaxies mirror those of the early universe's first galaxies. By understanding these small galaxies, we gain a unique window into the cosmos's past, a glimpse into the conditions that gave birth to the first galaxies. The research led by Michelle Jeckman and Sally Oey has thus opened up a new chapter in our understanding of the cosmos. Their findings shed light not only on the conditions that foster star formation in dwarf galaxies, but also on the early universe's first galaxies. In conclusion, the smallest galaxies in our universe are indeed the largest star factories, a fact that changes our perspective of the universe and its workings. As we continue to explore the cosmos, we're reminded that size doesn't always matter. And in the case of dwarf galaxies, it's their smallness that makes them truly stellar. Before we wrap up this cosmic journey, let's take a moment to appreciate the wonders of the universe that we've uncovered today. The small yet mighty dwarf galaxies with their bustling star factories have become our time machines, offering us a glimpse into the early universe's first galaxies. But our journey doesn't have to end here. There's so much more to explore, so many more celestial mysteries waiting to be unraveled. If you too are intrigued by the cosmos and its countless marvels, we invite you to join us on our journey of discovery. Space Origins, our YouTube channel, is your gateway to the universe. Here you'll find a wealth of information about the cosmos, fascinating insights into the latest research, and captivating visuals that will transport you to the farthest corners of the universe. If you've enjoyed our journey through the cosmos today, don't forget to subscribe to Space Origins. By doing so, you'll ensure that you never miss out on any of our exciting explorations. Let's continue this journey together, delving deeper into the mysteries of the cosmos, one star at a time. Thank you for watching, and until next time, keep looking up.